Okay, today we're going to talk about intermolecular forces, and I will upload this PowerPoint to Edmodo for you can also print off the PowerPoint if you'd like, or I could give you a copy if you come by. But we're going to talk about intermolecular forces and what an intermolecular force is. So that's our key, intermolecular force. Now, for about a year and a half in chemistry, we've been talking about a bond going on between atoms. So I want to get the difference between a bond and an intermolecular force with you. And so this little picture is a very good example of the difference between an intermolecular force and an intramolecular force, which we'll see on the next PowerPoint. Intra, with a T-R-A, intramolecular force is a force or a bond going on within the molecule itself. It's holding the molecule together, and we've learned it's either ionic or it's covalent. That's our choices, ionic or covalent, and that's going on within the molecule, and that is holding this hydrogen to this chlorine here. And this one right here is actually a covalent bond. And if we were to be real specific, it's actually a polar covalent bond because they're sharing their electrons, but chlorine's a little bit stingy, so he's pulling more of the electrons over towards him. So this is actually a polar compound here, and this bond in here is an intramolecular bond or intramolecular force. The inside over here between this hydrogen and this chlorine, they are actually connected to one another, and their electrons are going back and forth, back and forth. Now, what we've got going on here is a weaker force, and this is an intermolecular force. It's a slight attraction because because it's a polar molecule, is slightly negative. This one over here is slightly positive. There's this slight attraction. They're like married over here, and they're like married over here, and there's this attraction going on between these molecules. So it's a lot harder to break this bond here, this actual covalent bond. If we do that, we get a chemical reaction going on. When we break this bond in between here, or this attraction, this intermolecular force here, we actually do not get a chemical reaction. We actually see a physical change going on. We have things going from solid to a liquid. So you start breaking up those forces, you change the states of matter, and you see it going from a solid to a liquid, or maybe a liquid to a gas, etc. So what this is going to change in between here is we're going to see what's going to determine that is boiling points and melting points and freezing points. Those things right there are what affected all those physical changes, and the reason those take some energy, you have to break those bonds there. So the next slide says exactly what I just said. Enter the TER, molecular force, or the attractive forces between two separate molecules. Intra, on the other hand, is the forces that hold the atom itself together in a molecule. So this one's between two different molecules. This is inside the molecule itself. You can go back and look at that picture and you can make sense of that. Intra is either ionic or covalent, and that's what we've been talking about for 2 years. Now we're going to go a little bit different forces here. Some of the things that we're going to be looking at are some comparisons, if you'll notice here. For water, the intermolecular force that holds one molecule to another water molecule in order to make it go from liquid to gas, or we call that vaporize, it takes 41 kilojoules. On the other hand, in order to break the hydrogen and oxygen bond that's inside that covalent bond that's in there, it takes 930 kilojoules of energy. So a lot more energy to break that intermolecular bond going on instead of the intermolecular force. So some of the things that we'll be looking at, it says generally intermolecular forces are much weaker than intramolecular forces. We'll be looking at boiling points. We'll be looking at melting points. We'll be looking at heat of vaporization. We'll also be looking at heat of fusion, which is, again, that solid going to a liquid. We'll also be looking at sublimation. Heat of sublimation is taking it from a solid straight to a gas. So these are things that will be affected by intermolecular forces. There are 5 intermolecular forces, truly. We are only going to talk about 4. I will briefly mention number 3, but the ones that you need to know are number 1, number 2, number 4, and number 5. So you need 1, 2, 4, and 5 are the ones that you need to know. And these are listed from the strongest force to the weakest force. The strongest is between two ions. The second is something called hydrogen bonding. The third that I do not care that you know, but it's called ion dipole. This is things that dissolve into other things. We're going to be looking at something called dipole-dipole. And then we'll be looking at something called London forces, or sometimes called dispersion forces. This is just giving you a relative strength of kilojoules for breaking those bonds. So you can see the ionic and then the covalent. Then you've got hydrogen next. So ionic is going to be the strongest there. Alright, the first type is known as ion-ion. It is the force that holds one ion to another ion. And this technically is ionic bonding, because in ionic bonding there is that transfer of electrons, and then these things just stick together. They're not physically going, the electrons aren't physically going back and forth, back and forth, back and forth. They're not being shared. They've already moved, and then you get charged particles, and it's kind of like magnets stuck together. And in order to break these bonds, when we start breaking up these bonds, you start changing states of matter. And eventually, if you break all these bonds, you can start getting chemical reactions if they bond to something else. But this is a salt crystal in a solid form. If I start breaking a few of these, then I could actually make it liquid. Something that you need to know about an ion-ion compound, or an ionic compound. Let me get my pen out. You may want to write this down, because you do need to know this. And purple is probably not a good choice. Let's go something that you might can see. We'll go yellow on here. That in an ion-ion compound, at room temperature, these things are actually solid at room temperature. They're actually a brittle solid. If you think about salt crystals, ionic compounds mostly are what we call brittle, meaning that they form these crystals, and if we break these along the crystal lines, then we can break them. And they will not conduct electricity. They will not conduct electricity as a solid. I'm just going to shorten that to electricity as a solid. So salt does not conduct electricity as a solid. But we can make salt conduct electricity. One way salt will conduct electricity if we were to dissolve it in water. If we take, and water will dissolve ionic compounds for the most part, unless their KSP is really small. If you were to make them aqueous, they will conduct electricity. We call them electrolytes. Another way is if I were to break some of these bonds and some of these ions would get exposed, it will also conduct electricity. And we call that, if we were to melted form, there is a more scientific word for melted form. It's called the molten stage. So in molten, it will conduct electricity. So you do need to know that is a characteristic of ionic compounds. So that's the strongest. And so because this is the strongest, they're going to have the highest boiling point. They're going to have the highest melting point. They're also going to have the highest heat of vaporization. Heat of vaporization is the amount of energy it takes to send it from a liquid to a gas. So it's going to take a lot of energy for this. So ion-ion is the strongest. Our next one, if I can get it to click, is known as hydrogen bonding. And a lot of students have a misconception of hydrogen bonding. They think hydrogen bonding is any time hydrogen is bonded to anything. But honestly, it's not. It is actually specifically when hydrogen is bonded to oxygen, nitrogen, and fluorine. These three, nitrogen, oxygen, fluorine, I usually say NOF. And so if you've got a nitrogen, oxygen, fluorine, and a hydrogen, then there it becomes hydrogen bonding. What you need to understand, though, is that the hydrogen bonding is not here, because that is an intramolecular force. This is an intramolecular force. This is actually a covalent bond. This is a covalent bond. covalent bond, covalent bond. It's this attraction that this water molecule here has for this other water molecule sitting over there. And so this little attraction between this oxygen and this hydrogen is called a hydrogen bonding. It's because it's hydrogen and nitrogen, oxygen, or fluorine. And so you're looking at the hydrogen bonding occurring here. Notice this is ammonia and nitrogen to this hydrogen over here. Again, we're talking about intermolecular forces, not intra. So we're not talking about here because that's actually a covalent bond you're looking at there. We're talking about this slight force here. This is why water is liquid at room temperature. This is why water likes to stick to itself. And so that explains a lot. So hydrogen bonding is the second strongest. And so if we're looking at boiling point or freezing point, etc., or melting point, it is going to be the second in that list. A little worksheet, if you come by, if you haven't already picked up, it has you rank things on your quiz. You'll have to rank things. So if it has hydrogen bonding, it's going to be the second as far as the highest boiling point, melting point, etc. Alright, this is just going to explain that a little bit more. Hydrogen bonding requires hydrogen bonding to an electronegative element, the most important being nitrogen, oxygen, fluorine. The reasoning being is because that element is so electronegative that the electrons tend to be more on it, and it almost completely pull those electrons off, so it makes it like supercharged, and that supercharge is therefore making hydrogen bonding kind of really strong. Alright, the next one I'm going to go with, this is just again showing water molecules. The reason right in between this water molecule and this water molecule, we've got the intermolecular force there being hydrogen bonding. This is number 3 from that first list. It's called an ion dipole force. I told them I didn't really care for them to know much about this, but I wanted to explain it, and I'd actually seen it on the tax test before. But it explains, and this next one actually, the next picture, is going to be a little bit better. It explains why an ionic compound is attracted to a polar molecule. Anytime we have a polar molecule, which has a positive or negative side to it, it's said to have a dipole moment. A dipole moment is at moments it has a pole. Di means two, so it has two poles, a positive and negative. So every time I say dipole, I'm just talking about a polar substance. So we'll be talking about dipoles a lot. So dipole just means it has a positive and negative side to it. And the positive of this is actually attracted to the negative of this over here. And that attraction can actually, is the reason things can dissolve in water. This negative is actually going to be attracted to this positive. And so they'll align themselves this way. So this is two different compounds being attracted to one another. This picture shows it very nicely. It shows that the chlorine ion, if I can get this to go back and have my thing show up. Starboard's not wanting to cooperate. Well, you're just going to have to look yourself. I can't point, but the sodium ions, the positive, are actually being attracted to the negative part of the water molecule, and then the chlorine, which is the negative part of this of the salt, is being attracted to the positive ears. And if you'll notice, I really wish I could make my board work. There we go. I'll see if I can go. See if I can get it to go backwards. There we go. Do you know what's going on between this water molecule and this water molecule? This slight attraction here. That is hydrogen bonding going on here. This is not hydrogen bonding. This has hydrogen, but that's not a nitrogen, oxygen, and fluorine, so that's not hydrogen bonding either. This is just what we call an ion dipole, because that's a polar compound, so he's called a dipole. It's called an ion dipole interaction. But I would like to point out all this hydrogen bonding going on between the water molecules. Alright, the next is called a dipole-dipole force, and you will see this between polar compounds. So if the compound you're dealing with is polar, it will be attracted to another of its kind, and we call this a dipole-dipole force. And so a good example they're showing, that to me these look like Mike and Ike's, but if this had been like HCl and this had been HCl, the hydrogen and the chlorine will line up to the other hydrogen and chlorine, and so they'll stack themselves like this. So this would be a good example of a polar. Polar, we say dipole, dipole. So because it's a polar, which is a dipole, and a polar, which is a dipole. So this is a dipole, dipole. The force going on in between here. The force in here. Not the force here. This is actually a covalent compound here. The force between these two. It's kind of a weird looking picture here. It looks like a turkey to me. This is showing hydrochloric acid, or if we want to get real technical, hydrogen chloride gas. But if you've got a hydrogen and a chlorine here, this is a covalent bond. This is polar because this guy's going to pull. Remember, if it's linear and they're different elements, it's going to be polar. And he's going to pull the electrons this way. So this is a covalent compound. But because this guy's slightly positive and he's negative, this guy's negative and this guy's positive, there is this attraction going on between here. This is what's holding the two different molecules slightly together. And this is called a dipole attraction. And we just kind of break this up, and then we start changing states of matter. This is our third strongest type. So we had ion, strongest, highest boiling point, etc. And we have hydrogen second, and we have dipole third. Alright, this last one's called a dispersion force, sometimes referred to as a London dispersion. You can read about this in a book. I'll try to do the best I can to explain it. Everything has London dispersion. Ionic compounds have London dispersion. Hydrogen bonding compounds have London dispersion. Everything has London. But if the compound is nonpolar and it doesn't fit in any other category, the only thing it's got going for it is London dispersion. Okay, so everything has London, but some things only have London. And what London is a slight attraction one molecule has from the other. I gave the example, and they're going to talk about this little picture here. It talks about the electrons are moving really fast, and sometimes they're moving so fast that the molecule will get lopsided. So there might be an instant where there's more electrons on one side than the other, and that's what they're showing here with this lopsided thing here, that it got slightly lopsided. Maybe at a moment these electrons were hanging out more on this side. Because of this slight negative and this slight positive that's very instantaneous, that this I2 could actually be attracted to that other I2 down there, and that F2 could actually be attracted to that other F2 up there. So what you really need to know about London dispersion is everything has London, but if it's nonpolar, then that's all it's got going for it. Okay, what do you think would be have more London? Something that has less electrons or more electrons? And the answer is actually if it has more electrons. The more electrons, the more likely it is to get distorted. And the more likely it is to get distorted, because you think of those electrons running around, then it's going to have more London. So if you have London, the one with the greater mass is going to have more London. So you would, because the greater the mass, that means it has more protons, but if it has more protons, it also has more electrons involved. So if we were looking at I2 versus F2, that we're looking at on the sheet down here in the green, my thing's not wanting to point again, but if we were looking at those two and I asked which has more London dispersion, the I2 would have more because it has a greater mass. I2 weighs more than F2, so therefore it has more electrons. Alright, so we're going to quickly go through this. What type of intermolecular force would exist between each of the following molecules? And it's not talking about, let me minimize this. I guess we'll do yellow. It's not talking about this going to this. It's not talking about that covalent bond in there, because it's talking about this molecule here liking another one of its kind over here. Wants to know what kind of attraction would we have going on right there. And so we would go through our list. We would first start out with ion. In order for it to be ion, it has to be a metal and nonmetal. This is not a metal and nonmetal, so it is not an ion. The next we would look for would be hydrogen bonding. Okay, now this has hydrogen, but this hydrogen here is not being attracted to nitrogen, oxygen, or fluorine. It's being attracted to a bromine. So this is actually not hydrogen bonding going on here. Next, we would look for dipole. Dipole means the compound that you're dealing with is polar. Since these guys are linear and they're opposite, they're not the same element, this is actually a polar compound. And if that one's polar, this one over here is also polar because they're the same. And so because they're polar, we could say they have a dipole moment, a moment where they're going to have poles. So this is actually known as a dipole. this one here, CH4, if I draw him out, well, let me back up and we say, I won't erase because I am going to draw him out. We would look at him. Would he be an ion-ion? The answer would be no, because he's not a metal and a nonmetal. Our next thing, would it be hydrogen bonding? Well, there's a hydrogen there, but there's no nitrogen, oxygen, or fluorine, so no. So then you have to draw him out, and that's where you go 4 plus 1 times 4, put carbon in the middle, and you would draw this guy out the way we did with the one quiz. So I draw this out. Again, I'm not talking about what's going on right there. This is tetrahedral. This is nonpolar. We've got a nonpolar compound here. We're talking about him being attracted over here to this other guy. We want to talk about, well, we could just talk about this guy being attracted to that. There's some sort of attraction going on. So since this is nonpolar, this is nonpolar, the only thing that two nonpolar substances have is, we said this one was dipole-dipole. This one would be London dispersion. Alright, our next one, it's not ion-ion, it's not hydrogen, so I actually have to draw it out. This one's 6 and this one's 6 times 2, so you've got 12 plus you've got 18, so you would put him in the middle, you would do something kind of like this, and then you would put something like that. That's 16, we were trying to get to 18, so there's 16, we put 2 extra there, and we're still not happy, so now we would get out our eraser and we would take away and we would draw a double bond. This one's actually going to be a 3-1 bent, but can you see those electrons here? So, and again, I'm talking about him to another one of his kind here. I'll draw this one out in the correct shape. That one's not in the correct shape over there. And we're talking about an attraction going on here. And since this is a polar compound, polar, then this would again be a dipole-dipole. Okay, so once you kind of know them, then you can start putting them in some sort of order there. Alright, we're going to go to the last slide. I'll click through this real quickly. This is pretty much what that is saying. Alright, this one. It says both ICl and Br2 have the same number of atoms and approximately the same molecular weight, but ICl is solid, whereas Br2 is a liquid at 0 degrees and Y. So let's talk about this. Get my pen and then minimize that. If I drew out ICl, it only has the choice of being linear, because anytime you just have 2 elements, you're going to make it linear. I could do this. This is going to be 14. So there's 6. There's 6, and 6 is 12, 13, 14. This would also be 14. So it kind of looks like this. Alright. Oops. That's an R in there. So the difference is this right here is a polar compound. So if it were being attracted to another ICl, this one is nonpolar. So what these have going for them is London dispersion. What this has going for it is something called dipole-dipole. Okay, and this is a stronger intermolecular force, so therefore it's more likely to be solid. This is a weaker, so it's more likely to be a liquid, and even weaker, it's more likely to be a gas, and that kind of explains the forces that are holding them together. The stronger the force at room temperature, they're more likely to be a solid. So that leads us to our last thing, was talking about putting things in order, and that's again what the worksheet has. If you're looking for the highest melting point, boiling point, and it says this on the worksheet, or a heat of vaporization. You're looking for the one that would be the strongest bond. And it would go in order from ion-ion, hydrogen bonding, dipole-dipole, and intermolecular force, London being the last one. If you were looking for the highest, this one's opposite. This one's called highest vapor pressure. This is the pressure of it wanting to be a gas. It's trying to escape to a gas. This one actually is the weakest bond. So the London, the lowest mass London would actually have the highest vapor pressure. The lowest vapor pressure, the more likely to be a solid than a gas. These guys are more likely to be a gas. Are going to be your ion-ion. So these are in reverse order here. And that's what the worksheet is all about. Alright, that's pretty much the lesson and everything that I taught that particular day. So hopefully you could understand it. If not, you are going to have to come in because that's the only way I know to help you. So I've done my part. Your turn now.